build that scientific network, understand the modern science. That's what we do. Okay, so this is actually something very basic. And to understand when you have to go back to your basics. Okay, so we are going to do this and we will
Good morning and a warm welcome as we had our first session by Megha Rajoria. So now we have another the talk lineup, which is about citizen science research on galaxy evolution using GMRT and AstroSat by Dr. Ananda Hota. So let me also add him.
So should we start? You ready?
So, Planetarium is really privileged that Dr. Hota is with us today at the Planetarium because as earlier also shared that this RAD workshop, the fifth session on the line, which is designed in a manner so that people outside of the Delhi and from the Delhi can get the benefit of this collaboratory. So about Dr. Anand Hota, I would like to give a small introduction. He is an University Grant Commission UGC Assistant Professor, also heading RAD at Home Astronomy Collaboratory, which is hashtag RAD at Home India. RAD Home at India is the only Indian citizen science research platform in astronomy since 15th April 2013. It is a zero-funded, zero-infrastructure, national-wide inter-university collaboratory of 150 plus trained citizen scientists or e-astronomers and dozens of professional astronomers and thousands of online learners. Over 1,000 student citizens have been trained on the basic multi-wavelength, UV optical, IR, radio, extragalactic astronomy by RAD at home. So, Planetarium is also privileged that he is with us today, and students who got selected and can come to the planetarium will definitely get benefit to get hands-on learning experience within it. So over to you, uh, Dr. Anand Hota, sir.
Good morning, everybody. Can you hear me?
Yes, we can hear you, sir.
Great. Good morning again. It's kind of in a hybrid mode. For many weeks, we are learning online. Some of them, through that interaction, got selected to advanced level training. And today morning, we are sitting in a public talk live, free for everybody. So for this first two talks, everybody watching online or who will watch it later, they are all welcome to get entry into learning some amount of astronomy. I usually start my talks in a very unusual way. So let me give you a hint there that a lot of people think that astronomy is a basic science, fundamental science, abstract level thing. It is not useful. But can you tell me what is the date today? Can you tell me what is the time? So the very fundamental things of measuring position and measuring time are actually given by astronomy. So some way it has become so omnipresent in our life that we have taken it granted. And I tell the other round, when something is not actually useful for your roti kapda makan, that is useful to everybody's roti kapda makan actually. Basic science, like we teach many things, it becomes useful to everybody. I will start with my slides and I will explain more about all these things. Let me go to my slide. Can you see my screen? Prerna ji? Do you see my screen? Megha, go and confirm if you can see my screen.
Sir, we cannot see your screen.
Oh, I see. It is in mirror. Now?
Yeah, it's coming, sir. Please
Okay,
change
fine.
the slide so that we can say it's moving or not.
Yes.
Yes.
So let me formally start. So thank you very much, Nehru Planetarium, for inviting me to this talk, as well as arranging so that many people, hundreds of people can watch it. There is also a gathering here in front of me. We'll be interacting and learning something beyond what a slide presentation, what a YouTube talk can give. There is no comparison of physical face-to-face interaction with a teacher and then listening to a YouTube talk. That is why workshops are very different. So I've given the title of my talk, Citizen Science Research on Galaxy Evolution using GMRT and AstroSat. So I've been introduced by Prernaji. I don't need to explain more about me. What is more important is see the picture here. What is the picture? Left hand top, you see Nehru Planetarium's logo. Right hand top is Radiatom's logo. Then comes at the space itself, your AstroSat, which is our AstroSat. It's a multi-wavelength space telescope prepared by many Indian and some foreign institutions, launched by ISRO. It is not a single wavelength telescope, it observes in multiple wavelengths. India's first multi-wavelength observatory in that sense. Then comes a spiral galaxy's ultraviolet image. It's not an optical image, it is an ultraviolet image which you cannot see with your eye. Because this telescope is in space, there is no atmosphere, there is no absorption, so it can observe the ultraviolet. It actually observes the X-ray also. Then comes on the left and bottom our own GMRT image. There is again world class, both of this telescope. So what we will be describing today is according to my expertise that I can train you something and involve you in possible research. So the kind of publication that I can do with AstroSat and GMRT, that will be learning more. If you go and join some other research scientist, some other research group, you will be learning their skill and you will be able to produce science in their way. I cannot teach everything because I cannot do research on everything. I may be an astronomy teacher, I can teach many things, but cannot do research on everything. That is a specialized area that I can do. So to start, in Reg weather, apparently it is said, not apparently, it is said, some of you can read and some of cannot, but let me read that. Yatha sikha mayuranam, naganam manayo yatha, tadvat vedanga sastranam, jyotisam murdhani sthitam. Few words you can see. Sikha is like hair, head in the Mayur is peacock, Naganam, Naga is snake, Mani, like the precious stone. So the way at the apex of a peacock, colorful thing, top things are kept, like people believe money is kept on the top of a snake's head. Similarly, Vedanga, Sastrana means after Veda, whatever Shastras have been written, the apex or the most important, most highest respect is given to Jyotisam, means mathematical or positional astronomy. Why it is said that? The ultimate aim is not just Roti Kapda Makan. People, the civilization actually thinks beyond that. For example, who does not know that man has reached moon? It is the success of the civilization going beyond Earth. Sputnik, Apollo, all these things. I will give you another example. That is the Rig Vedic standard in those days. At the later stage of Sir C.V. Raman, our own very own only Nobel laureate in science, he was asked by somebody that suppose you take another birth, what will be the research topic that you would take? He replied, heard from many people, that I would work on astronomy. It is something like this year's Nobel Prize has been given to this paleogenetics scientist, right? From German origin or German working in Max Planck. Because who is your father, mother? Who is your forefather? How did we come from Homo sapien, Neanderthal, Denisovan, etc.? Understanding this origin is very critical. It touches the core of our heart, core of our brain, core of the thought process of the civilization. Similarly, where is our Earth? Where did it come from? How did the universe begin? How did the life begin? These questions are ultimate that everybody is trying to understand. So why I'm starting this? is actually this, that don't get confused about what is applied. For example, sports, everybody plays. Is it an applied thing? Astronomy, is it abstract? According to Nature magazine study, astronomy and this anthropology or the evolution of human, the most popular subjects. We all admire. There is something beyond this roti kapada makan always. So, without putting more argument, let me put a statement that I believe, and we are actually trying to do that. In astronomy, a lot of people have been saying, and you may have heard, that there is something called big data problem. That computers and telescopes are creating so much of data that even astronomers are not able to digest it or handle it appropriately. So there is so much of power that the data has already in astronomy. We believe that this big data problem of astronomical telescopes is actually a big opportunity for big nation like ours. If we adopt a Redatom-like citizen science collaboratory approach where the data can be distributed, the training can be made to the students and citizens of the country, they can use it for their personal career development or personal development, as well as they can contribute to the nation's development, as well as they can contribute to the civilization's growth towards astronomy. So that way, it's like astronomical data is raining everywhere. Gold coins are raining. It is only we don't know how to make use of it. So that is why citizen science is in the picture, that we can learn to use it and grow our career. I will give you a quick example that close to 160 Redatom citizen scientists have been trained for a week-long program, and more than 60 of them are actually pursuing astronomy, astrophysics PhD and space science PhD. How? This participation in Redatom has helped them present papers or publish papers or get recommendation letter, get training. For example, some Raman Research Institute professor has told me that students come to Raman Research Institute's training interview, and when they ask what astronomy have you learned, that student would say, I know RGB image analysis. Then the professor asks, oh, tell me, what is RGB image analysis? That is what is the literary starting of your learning astronomy. It is not the remembering astronomy fact, it is actually the skill to analyze something and create new knowledge. Research internships or research interviews are not to find out what you know, but to find out, do you have the attitude, do you have the skill to know new things? Okay, so with this kind of broad message, that astronomy is not just to learn, it is the way that if we skill ourselves, empower yourself, we can grow. That is why International Astronomical Union is having an office in South Africa, Astronomy for Development. And the same International Astronomical Union is also supporting Redatom so that we have our first international Redatom workshop. In December, we are having it. So this is my outline of my talk. I can give you what is the astronomy things we will be learning. I have already described, but briefly with slides, I will give justification for citizen science, how it is research plus education plus outreach. Then we'll go to the detail that most of you already know. We'll be looking at the UV, optical, IR, radio astronomy, looking at RGB image analysis. Then I will go a bit deeper. Then we'll talk about redshift, we'll talk about rotation curve, we'll talk about dark matter in galaxies and accretion onto black hole. Then people who are already selected for the afternoon session, they will be looking at DS9 and analyzing FITS files from AstroSat and GMRT. So hierarchically, not in this public session, everybody will get equal opportunity. You have to go step by step because hundreds of people cannot be trained equally. You have to qualify to the next level so that interactive learning will happen with us. Okay, so this is a quick thing, how Indian science has grown over several decades. A slide from a publication. The Raman, Bhabha, this kind of great leaders were there in the 1930 to 50, individual excellence. Then came how we can feed our people. Milk revolution, green revolution, white revolution, this all started. Technology denial, because it is important for defense. then IP generation, fighting for basmati rice, fighting for neem, fighting for haldi, etc. Today, we are at a different phase, globalized economy, that we have to lead. Otherwise, in defense as well as in economy, we will be lagging behind. So now today it's your turn not only to learn something from books and internet, but to create new things so that we can be better in life as well as we can be secure in our as a country. That is why having a skill is more important than just remembering what books have taught you. So ultimately, in single line, our aim is a faster, sustainable, and inclusive growth. We have to have at least we are in education and research, we have to have a model that is scalable for education and research. That is why involving large people and reaching up to the research excellence to publish a paper, both these things are equally important for a at-home collaboration. Putting things in perspective, what is there? There is a telescope, there is a microscope. We all know this is a telescope, this is astronomy. This is a microscope, this can be biology, physics, anything. But these things are educational toys. They are toys. They do not produce research results. They are too small. But we are always aiming at, for example, in astronomy, the first image of black holes accretion, Event Horizon Telescope created. We all jumped. This is wonderful. But with this telescope, you cannot create that kind of result. With a small telescope that you think of astronomy, we cannot create that kind of result. What do? What is the problem? That your schools and colleges are teaching you the basic things with the toy telescope. That's important. That is foundation. But at the same time, the time has come that not only we should learn education in universities and colleges, but be part of research some way. We always have to run something extra to be competitive in the life, in the career. So point is to understand black holes, to do research on black hole, you may be a toy telescope at home, but you also have a laptop through which you can join with Red at Home and be part of the research. So this is what is the message, that your education and toy telescope or the research facilities may be small, but through data science of astronomy and citizen science, you can reach the big goals. What are our big facilities? That was the toy telescope. These are our big facilities. They are not toy. These are giant machines, world-class telescopes. On the right-hand side, you can see the giant meteorwave radio telescope, GMRT. You can see a Tata Sumo-like vehicle here. You can see the size scale. Each dish antennas are 45-meter diameter. From one electric pole to another electric pole is roughly 50 meter. You can run and you get tired. But there are 30 such dishes spread over 25 kilometers. Megha already showed you in the previous talk. That is how the collecting area of each dish defines the collecting area, how much light, how much distance you can see, how much faint thing you can see from distant galaxies, correct? If you have a mobile phone photograph, if you have DSLR photograph, the qualities are different. This is because the photon collecting area is different for them. Similarly, the bigger the disk, bigger the number of radio wave or amount of radio wave, amount of electrical fluctuation from the radio waves coming from far away galaxy that is being collected. That's how we always want a bigger telescope to see objects closer to the Big Bang in some sense, far away in the universe, back in the history of time. Also, we want bigger telescope for better resolution, better angular resolution, so that you can see sharp thing. On the left-hand side, this is our AstroSat. In my childhood, I used to wonder, when there is no air in the space, why this kind of objects have wings. But they are not actually wings, right? You all know now. They are solar panels. So what is this AstroSat has many tubes and telescopes. Some are sensitive to X-ray, hard X-ray, soft X-ray. Some are sensitive to ultraviolet light. I mostly use ultraviolet light observations to look at galaxies. So using these two big things, we'll be doing some science. Here is a plot from Wikipedia in the bottom one, that the size of the optical telescopes and the countries and the time when they have been, they are all mapped. So it reflects that we do not have a big optical telescope. We do not have a world-class optical telescopes currently. 3.6 meter Devastal optical telescope is currently the largest one. And we are participating in 30-meter telescope, optical telescope project. So we should be using this world-class facilities that we have in our home, in our own country, use this and do some wonderful science. Combine all this data. That is what should be our edge. To define that we have a competitive edge of GMRT, this is the plot. The collecting area of various radio telescope, GMRT is here. 3 times bigger than the collecting area of VLA, most productive radio telescope in USA. So we have really a competitive edge there. This is the usage of astronomers of GMRT telescope. So you can see more than almost 50% time is used by Indian and the rest 50% used by foreign astronomers. That is what is so wonderful. That is it's an international competition to get time in GMRT. We at home got international time in GMRT also. So this kind of Megha described that these huge dishes are spread over 25 kilometers so that we have a world-class telescope here. You can satellite picture, you can see dishes there. From the Google Earth picture, you can see this is a reflecting light. From that GMRT, in 2011, I led a team to make some discoveries. Probably this was the first international news-breaking discovery from GMRT. What was that? A spiral host episodic radio galaxy. To give in brief, this kind of plasma jet that can be seen in radio comes out from elliptical galaxies almost always. We spotted the second and the first confirmed case of 2 such episodes happening from a spiral galaxy. Such an unusual and crazy stuff. That's why NRA, NSF, Royal Society, UK, many people gave press release and it came to the public notice. Very wonderful thing. There actually I thought that this is not such a difficult job to spot it, but it's a rare thing to spot. It's not difficult to spot, but rare to spot. So why not employ a large number of people in spotting such rare object? That's precisely was the idea. That the astronomy India's GMRT can be useful to larger public by training them, and they will be useful to science, and they are helping their own career by participating in some research that is important considered by the world astronomers. This is what is the starting time of the Radiotom's idea. How we can train large number of people and they be involved in the astronomy research. Recently he passed away. You heard from him, heard from Megha about him, Professor Govind Swarup. He appreciates that how larger number of people can be involved in scientific research with GMRT. You can read his statement here. Govind Swarup of NCRA, who was not part of this discovery team of the exotic galaxy specker. An outstanding discovery that is very important for cluster formation model and highlights the importance of sensitive observations at meter wavelength provided by the GMRT. GMRT is most sensitive to meter wavelength radio band. It is not sensitive to all wavelength. For example, radio telescope sensitive to radio, optical telescope to optical band only. So the sky is actually, the whole sky has been imaged by GMRT already at 150 megahertz or radio waves of 2 meter wavelength. That is when the starting point of my citizen science idea that I resigned my postdoc position and came back to India. That this is what is the right time I have to do now. That GMRT has produced all sky images. I am ready to train thousands of people who not only will understand what GMRT does, but who will be participating in discovering some rare objects, important objects using GMRT. So that discoveries happen from our own soil. When I say that was world class, that is because the collecting area, sensitivity, resolution, they are best. Similarly, our AstroSat is also best. See, for example, at the bottom, you can see NASA's Galaxy mission, ultraviolet image, black and white grayscale of some star forming region, and AstroSat image on the right bottom. You see the remarkable difference in the resolution. 3-4 times better imaging quality we have our AstroSat. That is the reason that astronomers from all the states all over India are learning to use and making discoveries. Astronauts from the whole world, US, Italy, Canada, you name it, they are all using it and trying to make discoveries. Discovering nearby star formation process to discovering far away high redshift galaxies. So this particular picture that I'm showing you now, we published in the special issue of Journal of Astronomy and Astrophysics and Astronomy, sorry. And the title of the paper you can read here, the sharpest of ultraviolet view of the star formation in an extreme environment of the nearest jellyfish galaxy, IC 3418. You probably can read many of my co-authors' name. At the bottom, you see the picture of the same thing. That there is a galaxy here, right hand top. It's an ultraviolet picture, false color of ultraviolet picture. Sharpest ultraviolet picture because we have resolution better than galaxy, NASA's galaxy. And this is the nearest object, such objects. So you automatically have the sharpest angular size picture. The galaxy is actually right hand top. When the galaxy moves to the diagonally up direction, the gas from this galaxy is actually stripped or pulled out of the galaxy, pushed out of the galaxy. For example, in a strong wind or a cyclone, the leaves from a tree is stripped, is removed from the tree, only the branch remain. So the galaxy will remain having only stars, very little gas. And the stripped gas that has gone out in the tail, lying in the tail, in that trail, the gas cloud will be coming close to each other under its own gravity. Probably turbulence also plays a role. When they come close to each other, gravity will be superseding and they will collapse and form new stars. Interestingly, the surrounding medium, actually million degree Kelvin, X-ray emitting hot gas plasma. But the clouds, when they are stripped, there is 100 degree Kelvin, 200 degree Kelvin, very cold, frozen like comet, that kind of gas. When they come out, they collapse, form star, and surrounding region is kind of burning with million degree. It's trying to ionize the gas. It's a very strange environment where the star formation is happening. Generally in our galaxy, there is gas that is like a blanket, is protecting us from the ionizing radiation of the surrounding. So stars are forming in the protected region. But this is a wild. The velocity at which the galaxies are moving is 1,000, 2,000 kilometers per second. High speed, high temperature difference. In such crazy environment, the stars are forming. And we're trying to understand what kind of strange star formation. Is there a new kind of star formation altogether? With the highest resolution using AstroSat, we try to study it. Actually, in 2013, when Rotational was launched, here exactly in this galaxy's one star, we spotted a blue supergiant star. Along with that news, actually, the launching of Rotational started spreading in 2013. So that is how Rotational is 9-year-old. Okay, so during all the last 10 year or 12 year or 15 year maybe, I kept on asking, what is India's competitive edge that we can become leader in science, like discovering decimal system, discovering zeros, etc., etc. The world have forgotten that we did it. Okay, so this was my ultimate answer, that if you want to lead science in the world stage, somehow we have to use these three aspects, combine these three aspects. Largest telescope, most sensitive telescope that we have has to be combined with this approach. That largest pool of science and technology manpower, largest pool of IT companies and engineers, largest number of mobile phone, computer, all talking in English and communicating through internet. Right? So this was the bottom line, that how can we have a man-machine combined system that we will use our competitive as the largest number of science and technology trained manpower. And this is the foundation of the citizen science program. So now that's what you see, that you have the largest radio telescope, largest number of trained manpower, and all the institutions that you see here. Some foreign institutions are also supporting. All the different institutions, Nehru Planetarium you can see here, today it is happening. But many institutions are supporting this kind of citizen science training program. Once you go through extensive training, then you will be plotted in this India map. These are the 160 astronomers. So they will be sitting at home after getting training from the institute every Saturday from 2 o'clock to 4 o'clock or any time they wish. They will be communicating with the group members that I have spotted something interesting, something exotic, something important radio source in the sky using GMRT data. Then the group members, their friends, will be discussing, no, you do check this, do check that. Only then it is important. When they finish that thing, it comes to me. Then I will carry my test as well as I will discuss with my professional astronomer collaborators. Then we will go to GMRT for further observation or we will go to direct publication. This is how the flow of discoveries actually happens. So this is basically in 5 points. The Red at Home has a website where things are documented. Like this is a website where you can get your RGB Maker tool. We have a Facebook group for discussion, social media discussion, which is free. Most people use. Discovery camps and workshops, read at different organizations, read at Nehru Planetarium today. Then we will have whatever you people find, we will go to GMRT, propose them this is an important finding, give us more time because you will be discovering from GMRT data that is taken only for 5 minutes. Now we will go and observe that target, that is potential discovery, for 5 hours. That is what is a good rack project at GMRT. GMRT observation of objects discovered by Astronomy Collaboratory. Once we do that, we are kind of empowered enough by the telescope. First 5 minutes, then 5-hour data with a world-class telescope that your important finding is worthy of publication in the international journal. Just wait for a couple of days. You will be at home will be having a press release of the important discovery by a citizen scientist like you, like one of you. So this is what we call a flying pyramid model. That you may be at the base, just learning astronomy analysis. Then slowly you grow hierarchically, contribute to a discovery. Your seniors will discuss, you will learn, and your super seniors will basically carry the discovery forward. We will publish it along with various other data and various other astronomers. The way you see, you all will be having a laptop trying to understand how to make sense of GMRT telescope's data. Once you spot something interesting and important, we'll carry it forward. Where we'll be discussing? We'll be discussing this 4,800 member group first, then there will be I astronomer group, and then be E astronomer group. Slowly, like filtering process, hierarchically, you will be growing. In the process, it can be a couple of years. So start with the BSc first year. You may have a paper. Even if you don't have a paper, you can still be useful. I will be giving a recommendation letter for your MS and PhD selection process. That is how we help astronomy and help you symbiotically. Okay, it's a representation of ICTS scan. I'm looking so that we don't dwell much on any single thing. This kind of selected people get trained for 7 days. Stay, food, everything becomes free. There are 3 camp has happened in Nehru Planetarium itself. We all stay here. We'll be bringing a person from Tamil Nadu and showing the fog and cold of Delhi. You'll be surprised that I'm still in the same India. It's really a national feeling has to come. Only then, if you know person to person, only then you help each other. I am stuck somewhere, a person will call you, video screen share and talk to you. One-day programs like happening today, 100 can be trained, as many as can understand. But interesting interactive learning happens only on face-to-face and smaller in number. Okay. This I have already described that professional astronomer collaborator, institutions, you are the large number of people learning RGB, then DS9, then DS9 discovery, and GTAC observation. Slowly we all grow. This is what is statistics that every Saturday interaction happens in the Facebook group. 100,000 posts, comments, keep on. Wherever you have free time, whenever you spotted something, you can post and discuss. This is how you get GMRT observation time as a co-investigator in the GMRT observation process. You get co-authorship, except the first few, everybody is like BSc, MSc student, a journalist, engineer, anything. This second paper. Within a few days, a third discovery is coming. Stay tuned with the Facebook page of Planetarium. You will get to know this. I have been felicitated by ISER, Barampur, Kolkata, Samanth Chandrasekhar Award. These are actually not just I'm hyping myself. This is what they are appreciating, that the new way of involving students and introducing them in science. This is a new way. That is why they are appreciating. The Mr. of Orissa. Okay. So as I told in the very beginning, what is the science focus? The science that I can do, the science that I have been leading. So see two papers here, SPECA I have already described. The second one was NGC 3801, a galaxy name, caught in the act. A post-merger star-forming early type galaxy with AGN jet feedback. The press release that I am telling, which will also something similar on AGN feedback, how AGN's outflow, the plasma outflow from black hole accretion process, affect the star formation in a galaxy, so that it is changing with time. The galaxy evolution it contributes to. That is called AGN feedback. AGN is active galactic nuclei. That means when the black hole is active and accreting gas or ejecting jet, whatever. So ultimately, when you join the RGB image analysis of at home, your purpose is to contribute something to this kind of papers. This kind of paper is this kind of a concept of science is very important. See, for example, square kilometer array. They have listed 1, 2, 3, 4, 5, 6, 7, 8. 8 different branches of science that is scar radio telescope is going to contribute. At one of them is galaxy evolution. That is very important now. How the building blocks for universe from early age to today it has evolved. We don't really understand it. You can see this NASA press release news of mine has appeared as an icon there. So many of you know that very simply we have a Python-based tool. Tomorrow, Avinash Kumar and Avinash CK will be coming, who are the main leaders behind this RGB maker. It is getting the data from 7 different FITS files through the NASA Skyview that has got from various other telescopes, like our GMRT has contributed to that data in radio. So you'll be looking at a particular galaxy in multiple wavelengths and trying to understand, given all this raining, gold coin raining data in astronomy, what you can find out the new way of connecting to the science that is considered important. Data is coming everywhere, in every wavelength, many wavelengths from many telescopes. How you can create a science that is considered important and you can publish as a paper, as a co-author there. That's the ultimate aim, galaxy evolution using multi-wavelength data. So purpose is that is why first learn how to make sense. Basically to recognize whether it is a white stone or a diamond, whether it is some yellowish shining metal or it is actually gold. Opportunity comes with a prepared mind. You have to be trained to spot it. You all have tried to do it. That we use Galax ultraviolet image, Spitzer's 22 micron image, and DSS optical image to make a UV optical IR or IOU RGB image of a galaxy. Similarly, radio 150 megahertz or 2 meter wavelength from GMRT India, and 20 centimeter or 1400 megahertz radio image again from VLA USA. So we'll combine with optical, radio, optical, radio. So we have a 1, 2, 3, 4, 5 different bands of information on the same galaxy to have a proper, complete understanding from the free data. This telescope has used 5 minutes only to look at one part of the sky. That is available in this RGB maker. If you spot something very important, then we'll go to GMRT again and say that no, 5 minutes is not enough. This is very important. Give us 5 hours and we'll observe for 5 hours. And then we'll see not just the tip of the iceberg that 5 minutes has seen, but the whole iceberg that is hidden inside the noise. Okay. Slowly coming to details in astronomy. We all know the moment we say astronomy, we look at stars and the constellations. But world has gone far beyond that. For example, here, we see the color of star. That is because the temperature, surface temperature of stars. All the stars can be considered like a black body. They are thermal systems. Stellar constellation. The moment you see gas and dust, it is scattered light or emitted light, absorbed light. The play happens, and you start seeing color in the nebula. Close to million stars can be there in a dwarf galaxy like SMC LMC. 100 billion stars will be there in a Milky Way galaxy like system. There will be gas, star, dust, and magnetic field, cosmic rays relativistically moving, the dark matter, black hole, various components of a galaxy. Now, here I have given a RGB picture, multi-wavelength picture. Pleiades, Kritika constellation, you can see the stars. If you go to stars, they are actually representing warm component of the universe or the sky. 6,000 degrees, 7,000 degrees, 4,000 degrees, and warm component. When the temperature increases, say to 20,000, then the peak of the emission will go to ultraviolet. This lambda max T equal to constant, this kind of means displacement law you have studied. So if you go that way, at 22 micron, the things which are frozen, 100 degree Kelvin, sub-zero temperature, 0 degree temperature, that kind of objects are radiating efficiently. So very cold stuff, warm stuff can be seen preferentially in different wavelengths. Now there is one more component that is not shown properly here. There are tiny contours, white contours. That is from the GMRT or the GMRT radio telescope. The contours are. What it is showing? GMRT does not show the bright stars or the cold gas, but it is seeing the non-thermal plasma being ejected by black hole accretion process in far away galaxies. Nearby stars it cannot see because a different emission process altogether. These far away galaxies are being seen. So we have a biggest telescope, radio, but this is a surprise that we don't see stars with this. So we have to learn something new that it is showing. It is showing the black holes outflow from far away galaxies. In this ROR images that we see, where our new things learning has started. Ultimately, we have to understand galaxy evolution. So how do you connect this black holes outflow to star formation in a galaxy, gas in a galaxy? That is what we have to learn. Okay. This is another picture just to surprise you. It's an O and B type star here, seen in green and blue. But the red thing that you see is a cold gas surrounding that. 100 degree Kelvin, 200 degree Kelvin. IOU RGB image. So the moment you go to other wavelength, you start seeing different component, different physical phenomena. Why this is curved? Because the star's wind is compressing on this side. The star is moving on that side. So that is why this is like a wake in a boat or a ship. You can see that curved surface there. So structure, color, and then start measuring the numbers in different wavelengths. That is how astrophysics starts. Earlier, these information were not there, so everything was only positional astronomy. But we have gone beyond that. A galaxy, Andromeda galaxy, just to give a snapshot. Here, optical picture, here, infrared picture, here, X-ray picture, combined. This is stars of the galaxy, dust, little bit of absorbing, looking brownish. Dust is silicates, micron size, and some blue region forming new stars. Okay, fine, we understand optical very easily. But the infrared, so as I said, 100 Kelvin, frozen stuff that is showing the dust and pH, polycyclic aromatic hydrocarbon. Where? This is in the spiral arms. How they are getting like that? Because the hot gas in the spiral arms are actually giving radiation that is being absorbed by the dust and being heated up and being re-emitted in infrared. For example, if you switch off the light in this room, I don't see you. I can't see you in the dark because my eyes are sensitive to only in the optical band. But if I have a thermometer in my hand, I can still measure your temperature. Keep it dark, doesn't matter. It will measure, right? Because it is sensing the infrared radiation coming from this 100-degree or 37-degree object's body. You are a black body, which is having temperature, fever or not, the thermometer can figure out. Similar to 100-degree Kelvin, few thousand-degree Kelvin, and this X-ray, million-degree Kelvin. So all frozen, warm, hot components can be seen in different bands. Now, let's try to understand this X-ray image a little bit. What is this X-ray image in blue? It is showing some diffuse, fuzzy, extended emission at the center and a lot of point sources all around. If you look at the galaxy's picture, combined picture, the point blue X-ray emitting sources are everywhere. What are they? They're actually X-ray binaries or neutron star and a star, that kind of combined system, black hole and a star combined system. When the matter from the star falls into the neutron star or black hole, it gets heated up at the center, it gives a lot of X-ray radiation. They are point sources because they're just around the neutron star or just around the black hole. So they are stellar mass, black holes, everywhere in the Andromeda galaxy. There are neutron stars and black hole which are of few times mass of our sun. They are too small, mass gas falls into them, gives X-ray. They are all these point sources. But the supermassive black hole that is at this very center of almost all galaxies, they are million to billion times mass of the sun. That we talk about, and that is the radiation that these spots are actually giving, tiny, tiny spots. So we are focusing on that because GMRT sees that. How that plasma outflow from the black hole will affect, that we will understand. This is another picture, ultraviolet, infrared, optical. What is the meaning? See, in the spiral arm structure, there are ultraviolet bright, 200-degree Kelvin, hot, massive O and B type stars. But the dust and pH is here. But the sun, like several billions of year old stars, are here. That is how we have started characterizing the structure, color, composition, age, evolution of a galaxy by looking at a RGB picture. Simple to make, we have tool, but the interpretation we are learning now that we can share in Facebook and discuss. Let's not go deep in there. Coming little bit of spectroscopy. That is the picture that you are analyzing. But how do you measure? By fitting the brightness in different wavelength, you are getting the temperature of the black body that is radiating. By fitting where the emission line is seen, for example, this is the spectrum from H alpha line, H beta line, H gamma line. The red, suppose this red line emitting H alpha, red light emitting H alpha line, the object that is giving light is running away from us. This can be red shifted, means this can go this way. Suppose this is blue shifted, this will be appearing somewhere there. So the location of the spectral line is giving us the information about the motion. Blue shift, red shift, at what velocity it is moving. From that motion measurement and size measurement, equating centripetal force, centrifugal force, we can start doing the mass measurements. Velocity, position, size, mass, temperature. This is how the physics measurement of astrophysical objects, astronomical objects had started. And one of the founders of astrophysics, you can say, is our own very own Meghnad Shah. So applying Doppler effect simply, that the wavelength at which you measure a spectral line's location compared to where it was supposed to be appearing, that gives us the velocity of set. That gives us the velocity at which the galaxy is going away from us, or that is the expansion of the universe. From there, we figure out the distance to the object. That object size and the distance to the object makes a triangle. And from there, whatever picture you are making, you can convert that angular size to a linear size. For example, if you take a photograph in this room, there is a cup, there is a person's face, there is a book. All the objects are having same number of pixels in the picture. That means they are of same angular size. Distance of that object from the mobile phone camera is creating different angular size for different objects. Different linear size, for example, linear size of moon and sun are very different. Lakhs kilometer, 1,000 kilometer value. But the angular size is roughly similar, half a degree angle. That is why the solar eclipse you can see. Interestingly, for lucky for us, the Earth people, that they are very different linear size, but same angular size. When the slightly difference happens, we see annular solar eclipse. Okay, let's have a distraction. Just for when the sun has come, I will tell you the H alpha line that you see from the sun in the morning and evening will be different. Because in the morning we are going towards the sun, in the evening we are going away from the sun. In the noon time, there is no offset. So this tiny difference in the velocity location gives you dynamics or kinematics of galaxies. Okay, so this is Hubble deep field. We'll close in 10 minutes or so that we can have some discussion. When you look at this Hubble deep field, it's very colloquially, I can say that you see your father photograph, your grandfather's photograph, and your own kid's photograph in the same thing. Some galaxies which are nearby, the light may have taken 2 billion years to reach us. For another galaxy, light may have taken 6 billion years to reach us, the Hubble Space Telescope. For another galaxy, it may have taken 10 billion years to reach us. If you sort them out in different boxes, the galaxy is 10 billion years light years away. The galaxy is 5 billion years away. The galaxy is 2 billion light years away. You can try to understand how do they different. Their star formation difference, their structure difference, their color difference. This is how you try to understand how the galaxies in our universe have been evolving with time. And this is what is the galaxy evolution topic. That when you have the opportunity, because of finite speed of light, to see galaxies at different cosmological epoch of our universe, can we understand how they are evolving and what are the physical processes that drive their evolution? As I showed you, if we observe this thing in non-optical band, this is optical picture, color picture, but optical picture. If we observe them in non-optical band, ultraviolet band or radio band, infrared band. So infrared band, you'll be seeing cold, old, long-lived stars. In UV band, you'll be seeing hot, massive, young stars. In radio, you will not see the star, but you will see the outflow from the central black hole accretion process. So various pieces of the puzzle basically need to combine and make a story or figure out a story that is important for everybody. Okay, this we have talked, but give you another way of looking at radio data. It is not just the plasma outflow from the black hole that radio telescope sees. It also sees something called 21 centimeter atomic hydrogen line. That means a proton and an electron in the ground state, they are neutral, they are not excited, they are ground, but they still have two energy state quantum mechanically. Parallel spin and anti-parallel spin. So the neutral atomic hydrogen in ground state also wants to flip from the parallel spin higher energy state to anti-parallel spin lower energy state. And that difference in energy del E is equal to H2 or Hc by lambda. That particular line emission like thing, that emission will come as a spectral line that comes very low in energy, that appears in the radio band in 1400 megahertz band. There our GMRT can see the wavelengths around 21 centimeter. So here is a picture in the screen, optical galaxy of a spiral, optical picture of a spiral galaxy, and 21 centimeter line emission or neutral hydrogen emission picture of the same galaxy. When it is radiated when the parallel spin has become anti-parallel spin, neutral atomic hydrogen. So what you can see, beyond the warm stars of the galaxy, there is a lot of gas that is seen around it. Because the gravity, that gas is just rotating around and trying to fall. So stars tell different story, gas tell different story. So all the stories have to be merged together to make a, this is what the picture actually. So looking at that line, which is supposed to come around 21 centimeter, if you look at one side of the galaxy and the other side of the galaxy, there will be slight different in frequency that it is accuracy. For example, your FM radio channels, 90.1, 90.3, they are different. Radio Mirchi, Radio Hot, or something. So similarly, radio telescopes tune into different frequency and figure out at what velocity which part of the galaxy is going away or coming towards us. That means if this is seen, say at zero velocity, the center, right side could be 200 kilometer per second going away, bottom side could be 200 kilometer per second coming towards me. That way, how far, the r, and the radial velocity v. You have a measurement of this galaxy now. R and v. You can estimate m. This is how you measure the dynamical mass of galaxies. Very simple. So from simple spectroscopic line observation of this gas in this spiral galaxy, you can determine its mass, dynamical mass or total mass. How much light is coming from the stars, you can have a scaling relation and estimate how much mass is there that is giving light. How much mass is there that is giving light, and how much mass is there that is making the galaxy's gas and stars rotate. Dynamical mass. The difference between them is actually the dark matter in the galaxy. So the way galaxy is rotating, it say for example, it starts with 10 km per second, 20 km per second, 100 km per second, 200 km per second, 250 km per second. So if you keep on going outside, the velocity reaches a level, and after that it remains flat. That is called flat rotation curve. I must be having a picture. This is what is the picture. Rotational velocity in kilometer per second, the distance from the center of the galaxy. If you keep on going outside the center, the velocity increases. Think yourself, what is the velocity at which Mercury, Venus, Earth will be going around the sun? Is it static? Is it increasing? Is it decreasing? Check yourself. So from here, basically, how the visible versus dark matter, total versus visible matter distribution is made in the galaxy is inferred. A lady scientist called Vera Rubin, she has done pioneering work and established almost that dark matter is there in every spiral galaxy rotating because their rotation curves are flat everywhere. This would have got Nobel Prize also. A lot of people believe that. So what we are trying to understand that we have not only appreciated the structure and color of galaxy images in multiple wavelength. Now beyond that RGB images, we need to know the velocity field. We need to know the redshift. We need to know the positions, mass measurement, temperature measurement, etc. So we'll finish in a few minutes. We have no time to go to many other details, but let me go quickly. That spiral galaxies where stars are forming currently in the gas-rich spiral arm, and elliptical galaxies which are not forming new stars for several billions of years. Understanding this by looking at the outflow from elliptical galaxy that can be seen in radio and studying the star formation history of those galaxies in ultraviolet is ultimate aim. And by looking at data in multiple wavelengths and interpreting their RGB images, we are trying to contribute to galaxy evolution studies. Okay, we have no time, but we are trying to contribute to galaxy evolution studies. The way brightness is distributed in different wavelength, that tells the age of stars in a galaxy. Looking at low frequency and high frequency radiation in radio, we see the RGB picture of galaxies. We see the outflow history of black hole archaeology. Once you learn how to interpret RGB images, we'll be able to grow further and we'll be able to connect. So what we, in summary, data is free from many telescopes. You need to learn how to download, read, make sense of it, discuss in a group, find out if it is an important finding. Then if it is an important finding, it is possible that you can be a co-author in papers. That is one way, very new way of citizen science collaboratory research, that you can help your career grow and contribute to the knowledge of human civilization about the universe. Thank you very much.
Thank you, Dr. Ananda Hota, for sharing this presentation. And also, we got one question during the live.
Yes.
So, Gagan Arora would like to ask, I have a question. Why the image taken by radio telescope have colors?
Okay. See, to represent a invisible wavelength picture, how do you represent? You have to give a color to show it. For example, if I show you a picture of a person's body in optical band, in the same picture I want to display where are the bones. How do you represent? You can put a black and white picture of optical picture. You can put a red paint and say that this is where the bones are. So we are sensitive to only few colors. So we code them red, green, blue, depend on different wavelength image. If you have single wavelength image, you can code them bright and faint depending on bright or faint. So multi-wavelength images are, that is why it is easier to give them a color code red, green, blue. Beyond optical, there is no color otherwise. It is invisible. Okay, any other question?
No, sir, we only have one question via online and also one message by Abhimanyu.
Yes.
That good morning, sir. We can hear you loud and clear. Thanks for organizing it in a hybrid mode. I am able to connect from Kuwait. So I think coming with this hybrid mode altogether makes some sense, because then it also get given the opportunity to people who are not physically come
Cannot travel.
at the planetarium to uh, gain the expertise in this area are able to do this. So we are really happy that towards coming towards the end, students, the participants are giving such messages.
Yeah. I will take some questions from here.
Yes.
Okay. And I will
So
repeat
meanwhile,
so that
anyone coming on, any students who are present online, if they have something, please drop in the chat box. Yes, we got one more
So
question,
I
sir.
take this question. So you explain why
Faizana,
it works.
how dark matter
So one
contributes
was
to the spectrum of galaxy.
okay, ask again. Read
How
that.
dark matter contributes to the spectrum of galaxy.
Okay. So I don't know what is there in your mind. The spectrum means that the line radiated in a particular frequency, it will be affected by the gravity of whatever is nearby. So suppose there is dark matter in a galaxy, less or high, that will determine how fast the galaxy will be rotating. So that way, a slow rotating body and a fast rotating body will have different redshift and blue shift. So I'm not sure if you are asking this. If that is your answer, that dark matter, high or low, amount of dark matter decides at what will be the redshift and blue shift. That is the effect on the spectrum. If you are asking the other way around, the spectrum over the broader wavelength, X-ray, UV, optical, then we do not have any radiation from dark matter. We do not know what it is made of. Is it made of electron, proton, normal matter, some exotic matter? We do not really know. What we only know that its presence because it affects gravitationally. More than that, we don't know. I
So we
think
really
that should be.
hope, Fazana, if you are looking for this answer only and any other clarification you need, kindly drop in the chat. We'll take it later.
If any other online question, I will address. Otherwise, I will go to the physical people here.
Yes, we have one more.
Yeah.
Sukhvinder Kaur, why jets from spiral galaxy so rare?
One of my pet question, you can call it. See, to launch this kind of large radio jets, which goes orders of magnitude far from the galaxies itself, you need a massive and spinning black hole. That the theory says that you need a massive black hole, you need a spinning black hole, so that the plasma that is launched from there goes to far away distance. So, how do you have a spinning and massive black hole at the center of a galaxy? How do you have a spinning and massive black hole at the center of a galaxy? You have small black holes in every normal galaxy. For example, our Milky Way galaxy has a black hole which is million times mass of our sun, few million times. How do you grow? Black hole will grow in their mass. Black hole will grow in their mass. Black hole will grow in their mass by accreting gas, accreting stars. At what rate they can accrete? Say at most one sun-like stars per year. So it will be very slow growth of black hole. That doesn't help much. The process is rather let's merge two black holes and to become one. Like gravitational waves are detected in that process. So black hole merger, how it will happen? Black holes are sitting inside galaxies, so galaxies will also have to merge. So when you merge two spiral galaxies, galaxies will also be merged, the stars in them become one system, the black hole will also merge, and they will keep on growing by accretion. So in that process, black hole's mass grows and black hole's spin grows by revolving around that. That is how you have a central engine, massive, powerful central engine in elliptical galaxies, which are products of mergers. It's common, that's why that all the jets are launched from elliptical galaxies, which are product of spiral galaxies merger. But when the spiral galaxy was found with a large jet, that probably rare, but it happens that from the early days, gas can be kept on accreting in a lonely spiral galaxy, which is already massive. It can probably grow big and launch jet. Its process probability is low, that is why it is rarely found, but it is not zero. It do happen sometime. And after discovery of Speca, there are some 5, 6 more spiral host large radio galaxies have been spotted. There is a more than 50% contribution from Indian astronomer in this field, not only because of me, but there are teams led by Viresh Singh and Joydeep Bagchi. Anything else online?
No online questions, sir. I think we can wrap up this session and we can take offline questions and then we can move ahead
Yeah.
with the other things.
Let me take offline question. Let the online
Yes,
people
yes,
listen to that
yes.
also.
So I'll just wind up here online so that we can go ahead with the
Huh.
offline.
Huh. He was asking first. Yeah.
So I was asking
All right. Thank you everyone for joining.
your team takes a picture, and if he finds something or she finds something interesting in that,